Good afternoon. I'm the CEO of Carrousel Digital. I'm going to talk you to a new IP, which is a radar, a quantum radar. Yeah. So the difference with the other radars, and even the radars which say they are quantum radars, is that we work by detecting the photon absorption. So it means we don't need any reflection. So this can work up to 300 kilometers. It's very good at detecting anti-reflective surfaces because they are very good at absorbing light. It's very compact. It's difficult to detect. And it naturally ignores the background, so it means that if you use it from a satellite, for instance, you can look at whatever object is flying below a certain altitude or above a certain altitude. It's good at detecting low-flying objects as well, such as drones. It can be color sensitive. It can see through fire. And even it's not there on the slideshow because I've updated it, so something went wrong. You can use it in the X-ray domain for body scanning, for instance. So how does it work? It works with entangled photons, and so we send a pair of entangled photons. One is going towards a birefringence crystal, which is going to split the photon. Photon is an electromagnetic wave into two at 45 degrees to the linear polarization of the original photon. So we send one bit to the sky and one bit to the possible object. Now, the entangled photon is being sent to a light amplifier, and the polarization analyzer. So, what happens? Let's say there is no object. In fact, the photon, even though it's being split, is not going to be detected anywhere before its sister photon is being amplified and its polarization detected, which means that the polarization of the sister photon is not changed from its original polarization. Now, second case, there is an object that is on the path of the half first photon. Well, the photon, every second photon, I mean, every two photons, I mean, will hurt the object, and will hurt this object with a polarization of 45 degrees to the original polarization. This will affect the polarization of the entangled photon, while if every other photon that goes to the sky goes without touching the object, the polarization of the second photon will not be changed, amended. So what happens is that by looking at every different, if the polarization on the second photon, we can see whether there was an object on the first photon. So of course, you see there is no reflection. So this is what I've just said. Now we can measure the distance because we can vary the length of the path of the second photon. So we can see whether the first photon is being absorbed before such or such length. And we can have a very good precise measurement because, for instance, we can have many different sets of switches, sending the second photons through different lengths. So for instance, the first batch would be fibers of 10 to 100 kilometers, so 10 fibers. The second batch would be 1 to 10 kilometers. The third batch would be 100 meters to 1 kilometer, unable to achieve a precision of 100 meters. Of course, we can make that more precise. So the advantage of this technique is that the wavelengths are customizable, and that the entangled photons do not need to be of the same wavelength. So, for instance, we can emit some photon on one side in the green, and another side in the red, or one would be a microwave, the other one would be a visible light. One would be so microwave is what is being used by classical radars. One could be infrared, the other one could be normal light. Infrared is very good because it's being detected by plastics. For instance, drones and planes with anti-reflective surface. The third, we can use different visible wavelengths to detect which colors are being absorbed most by the target, to find out what color is our target. And we can even use X-rays, because we can entangle X-rays to visible light photons for health or for ground inspection. Use cases. So firefighting, because in fact you can see through fire, because you send your photon, you don't really care about if there's any other photon going to you. Night vision, especially with color. Underground scanning, building structures, radio at airports, drones, sky radar, and of course cars. So what we do at Carrousel is that we design IPs and we patent them. So for this one we have registered a patent, but it hasn't been granted yet. But we had we've been granted many other patents in different domains. So one is using classical communication using entangled photons. We have a quantum secure signature. We have one-time pads distribution through the internet. We have a very interesting hyperbolic geolocation for indoor-outdoor geolocation, which is an alternative to the GPS. So it's not really quantum, but it should work pretty well. It works by using UHF wavelengths and working the time difference of light from the emitters to the receptor, and so the receptor doesn't have to be synchronized with any emitter. And we can achieve up to 50 centimeter precision. And another advantage to that it's different from GPS is that we don't need any satellite, and also the wavelength goes indoor. We have another one on long distance EPR channel. Most EPR channels which are made to achieve quantum teleportation are relatively short distance. Here with this we can achieve long distance communication, like 200 kilometers with fibers. We have another one which is screen blurring upon eyes approaching a screen. So what basically is that if your camera detects that someone comes in close to the line of sight of your pin pad or your screen, it will blur the screen. We have chip security for one-time pads to make sure that the precious one-time pads are being erased if your firmware is erased by a hacker. We have a chaining of offline transactions. That's very interesting for performing cache transactions when you are offline. For instance, when a network breaks. We have a passive photonic router for forming a hub linking multiple optical clients together. which is very good for optical communication. And then we are also a bit busy on energy. So it's a case use for radar. You have any question?
So can you go back to the principle, please? So how do you split a photon into two?
You put it through a birefringent signal, a crystal. So it's a crystal which has different...
No, but is this a single photon?
Yeah.
But you cannot split a single photon into two.
Well, it's, a photon is a wave. So a wave is delocalized.
No, a photon is... No. If it's in a photon case, it's not the wave case. So what you have is...
I'm sorry, you don't understand the situation. A photon is a wave. It's just that when the photon is being detected, it collapses into one point. That's about it.
Yes, but what you're talking about is the probability of finding the photon on the right-hand side or the left-hand side. There's only one photon.
No, you
There's
haven't
no
understood.
two photons.
It's not the probability.
No,
we know the probability.
Understand.
We know the probability, sir. I mean... do you have another?
This is quantum mechanics. So unless you're
it's not quantum mechanics, it's photonics. Excuse me.
No. You cannot make a single.
Do you have another question?
Two photons out of a single photon, unless you have a nonlinear material.
Do you have another question?
I didn't understand, I guess. Thank you.
I saw some applications in the underground. So what kind of depth you can go? It's shallow or deep?
It's the depth at which the X-rays can penetrate the ground, basically.
Okay.
So it depends on your material. If the material is heavy, they're gonna be more likely to be blocked.
We are speaking about rocks, for example.
I'm not a specialist on which rock, but usually it depends really on the atoms. Heavy atoms will absorb more easily the X-rays. So yes. Sorry, I can't have more precision. Yeah.
So you were saying here that what you would be measuring on the right-hand side would be a change in polarization. So how would you know that the polarization is coming from the object that you were trying to sense and not just from other things that were in the way? Is there a specific...
Sorry, can you read? Yeah.
As in, like, wouldn't the photons also get scattered by other things in the way between your...
Yeah, it's a possibility, absolutely. So, I mean, between the photometer and the birefringent signal, there's no scattering. It's going to transit through usually an optical fiber. But after that, yes. But this being said, you have to remember that people can establish optical links infrared between satellites and the ground. So it means that the photon is not scattered too much. Of course, there is a probability. If the object is smaller than the scattered photon, then you have to look at probabilities. Does it make sense? Or?
Thank you very much. What is the limit for your 300 kilometer? Like, why you can go higher? Is it the fact of the entanglement, or if you go to other wavelength, like if you go to mid-infrared that can fly, is it really like the light, or it's your entanglement?
No, it's a good question. It's because if you use optical fibers for the second photon, usually after 100 kilometers, they lose about 99 decibels. So now if you use a better fiber, or if you're happy to launch more photons, you could go a bit further.
Okay.
If there are no more questions, let's thank the speaker again.